All right, so today we're going to talk about related rates. And in this section, the important thing to remember is that when we take the derivative of something, we need to take it with respect to the variable that we're considering is changing. And up to this point, we've only had one variable changing, and that variable changing has been dx, or not dx, but x. And so we've taken, d dx, which means the derivative of something with respect to x. And at this point, we're going to change that because now we're going to talk about related rates, and rate has to do with per unit of time of some sort. And so when we take these derivatives, you're going to notice that the bottom is no longer dx, but rather dt, which means both variables are changing at the same time, not at the same rate, but at the same time. And what that means is we have to use our implicit differentiation because we can't definitely define or explicitly define any variable. So when we do this, we're going to take the derivative with respect to time. So now we're going to dv dt, both sides. Now pi over 3 is a constant, and in order to take the derivative of these two pieces, we need to actually use the chain rule and product property and power rule. So I'm going to pull out the constant, take the derivative of the first times the second, plus the derivative of the second times the first. Okay, so there's our derivative. That's dv dt. And what that means is the rate at which the volume is changing with respect to time. This is the rate at which the radius is changing with respect to time, and this is the rate at which the height is changing with respect to time. Okay? So, this is what we're going to be doing today, and I'm going to break this lesson up into 2 days. So the first day we're going to do level 1, baby step level 2 problems, and then on the second day we're going to hit the full-blown calc problems, okay? So suppose x and y are differentiable functions, which means they're changing. They can be derivatized, or you can take the derivative of both quantities, smooth continuous curves, okay? Both functions of t and are related by the equation y equals x cubed. Find dy dt at time t equals 1 if x equals 2 and dx dt equals 4 and that at time t equals 1. So what we're going to do is we're going to take the derivative. That's a lot of information here. And so I'm going to list out my knowns over here because I'm going to eventually do a direct substitution. So dy dt at t equals 1 is what I'm looking for. This is what I don't know. But I do know this. X equals 2 and dx dt at t equals 1 is equal to 4. So t equals 1, t equals 1, and I'm finding it at time t equals 1, so t equals 1. So I'm going to set up my equation, and now I'm going to take the derivative of both pieces with respect to time. So dy dt is equal to, now I'm going to take the derivative of x cubed, which I would have done before, same way. But now chain rule gives me dx dt. And now I want to plug in everything I do know. Well, at time t equals 1, I know that x equals 2, so I'm going to plug in some direct substitution here. And I know that dx dt is equal to 4. So dy dt has got to be equal to 4 times 4 is 16 times 3 is 48. Now my notation right there says dy dt at time t equals 1 is equal to 48. Now at this point I do not have any units, and so the rate of change is just 48. Something per something, I don't know. I don't know the units, so I don't include units. Okay? Important concepts here. The dx dt. Up to this point, the derivative of x has been 1. Dx dx is 1. And now we're changing that to be in relation to time. So we have got to keep both of these present. All right, let's do one more example. Okay, so oil is spilled from a ruptured tanker, and it's going to spread out in a magnificently circular pattern. That's kind of not going to happen, but we're going to assume that it happens. So a circular pattern whose radius is increasing at a constant rate. Oh, my board. Let's give it a second. Equals. Now I have units. Now a couple of things I'm going to point out here. It says it's increasing, so this rate should be positive, because positive means increasing, and so we're growing in size. So dRdt is actually increasing at 2 feet per second. So how fast is the area of the spill increasing when the radius of the spill is 60 feet? Okay, so all I did was read through the question once, and so now we're going to read through the question again and see if there's anything else I can pull out. Assume that oil spilled from a ruptured tanker spreads in a circular pattern. Circular. So I'm thinking circle, hence the picture right here. Circular pattern. Whose radius increases at a constant rate. How fast is the area? Okay. Of the spill increasing, so I'm actually looking for dAdt. I'm looking for the rate at which the area is increasing with respect to time, okay? And I want to find that at a specific instant when the radius is exactly 60 feet. So now I have to do some thinking on my own, because in order to find dAdt, which is what I'm looking for, I need to know what A is. So hello, important information from geometry. Welcome to calculus. What's the area of a circle? Quickly. Yes, pi r squared. Okay, so if I know that the area of a circle is pi r squared, then pi is a constant. So the only thing I have to take the derivative of is the radius component. So power rule, chain rule, and now I plug in the given information. So I'm going to use some markers here. Look, direct substitution, plug it in. Direct substitution, plug it in. Okay, so now when I do my math, pi times 2 times 60 times 2. Okay, and I'm going to not use a calculator, and I'm going to get 240 pi. Now I need my units, because now I've given units, I need to define my rate of increase of area with respect to the units I'm given. So this was in feet, and this was in feet per second. So the rate of increase of the area of the circle is 240 pi square feet per second. That means the area is increasing by 240 pi square feet every single second. So my final answer is 240 pi square feet per second. That is the rate of change of area for the circle. Okay? So now you can go ahead and watch the next problem if you want, but I'm going to stop here for day 1, because all I want us to do on day 1 is be able to solve some equations that only have 2 variables and that we can use with direct substitution. So here on this slide, you're going to see a strategy for solving related rate problems, and it gives you a fairly good process to follow. a couple of things are going to need to be consistent. You're going to need to read the problem more than once. You're going to need to list the knowns. It's very important to list the known quantities, okay? If you look at step 1, it says give a definition for each letter, which means if I say that y on my picture is this side of a triangle, or y is the height, I want to make sure that I label that. I don't just want to say, like say I had a triangle, and I call this h. I also want to say height of the flagpole, right? And this is going to help me, first off, visually represent my picture, but also it'll help me give my variables a relationship to each other, so that when I'm coming up with equations, and many of these are going to need a system of equations, when I'm coming up with the equations, I will be able to say, oh yeah, here's what I know from algebra, here's what I know from geometry. That becomes a super important step, okay? So at this point right now, I'm going to put up the problem set for my kids. Mr. Clinton's class, double check with him. We also have an additional handout. But at this point, I want you to go ahead and get to your book. I want you to go to page 208 to 209. And for day 1 problems, the quick check, you can do number 1 and 2. So quick check, I'm going to write it here. And that's on the last slide, quick check 1 and 2, but I only want you to do quick check 1 and 2 for tonight. On the 3.4 lesson B, you can do the quick check 3 and 4, but for day 1, just quick check 1 and 2. And then I want you to do numbers 1 through 4. Those are the only ones that we need to worry about today, okay? And this is, again, it's on page 208 through 209. These are the actual exercises. Okay, we're only looking at 1 through 4, and then quick check 1 and 2. Again, the quick check 1 and 2 is on the last slide. Okay? Tomorrow night, we'll have 3.4b, where we'll go through a couple more examples that are a little higher level thinking. Okay? I want you to practice these. Go back if there's anything you're confused on. Be ready to ask questions tomorrow in class. Good luck.